Okay, so I guess that you can see my screen right now. Okay, so good morning, everyone. So today I'm going to give a very brief introduction about earthquake and tectonic deformation associated with Myanmar and the northern Sunda Plate. So in this talk, I'm going to brief introduce several big earthquakes and the plate tectonic around the Eastern Himalayan Syntaxis, as well as what may be the root or the cause of those deformations. As we all know that around Myanmar, from Bangladesh to India to northern Thailand, there are a lot of active fault in this area. So the current map on your screen is showing that how this fault looks like in the span of the Southeast Asia. So that you can see that of course in the central Myanmar we have the Sangay fault, and in the western Myanmar we have the northern extension of the Sunda megathrust, and here we can call it the Rakhine Trench or Rakhine Trough. And to the north we have the Himalaya frontal thrust, and to the east we have a bunch of the strike-free fault systems. So today our focus will not be the Sangay fault in the middle, nor the western Sunda megathrust to the west. We are going to look at some very important event in north of the Myanmar, at the northern tip of Myanmar, as well as some important event in the Shillong Plateau and also in the Shan Plateau area. So before we talk about, let me change the. Before we talk about the earthquakes in this area, so everyone has already known that the current active tectonic of Myanmar is deeply related to the north motion of the India plate. So when the India plate is colliding with the Eurasia plate, it actually creates the current sitting of the tectonic framework in this area. And the Myanmar is around here, so it is deeply affected by the eastern margin of this collision system. And back to about 20 years ago, we always use this kind of a map to using this kind of map to represent the northward motion of the India plate. And what you can see is that the plate motion is the rate of plate motion, in fact, are decreasing from around 80 million years ago to about 40 million years ago. And there is a dramatic drop of the plate motion rate happening around 50 million years ago. And this is because that around 50 million years ago, the entire convergence system was changing from the subduction dominant system into the collision dominant system. And the Tibetan Plateau and also the Shan Plateau was a result of this collision process. So the computer technique starting to be more advanced, and now we can use a very good, we can try to compile all of the different information and try to make such kind of plate motion model since the, say, 500 million years ago or 250 million years ago. So this animation to the left is going to show you how we believe the tectonic motion looks like in the focus of the Southeast Asia. So you can see that everything is starting from the closure of Tethys Ocean, and also the expansion of the Neo Tethys, and the Australia, I think, is right around here, and this is the sliver now, like we call it the Myanmar sliver, and here there are several land blocks that are being slightly colliding into the Eurasia plate. And starting from about 80 million years ago, the India plate is moving toward the north very fast and forming several different sutures in between. and around 50 million years is starting to gliding into the Eurasia, and you can see this part of the crust is under the contraction, while this part of crust is under stretching. Now let's move. So this kind of phenomena has been discovered for a very long time. For example, everyone has already seen this very well-known map that drawn by Tectonic and when he doing his in his early career, that he believed that the northward motion of India continent actually created escaping tectonics in the from the central to the East Asia. So the orange patch, it's the Sunda Plate block, which in fact is it's an earlier extrusion block that extruded to the southeast when the Indian plate is moving to the north, gliding to the Eurasias. And once the Sunda Plate block moved to its roughly current location, the indentation of the Indian plate is moving to the interior of the Eurasia plate and starting the second phase of the extrusion, which led the southern China block starting to move eastward. So to form this kind of deformation, usually what we need is a very thick continental crust that with a very high rigidity, so that most of the motion, in fact, are accumulate along the major plate boundary fault, rather than having the strain or the deformation distributed in the middle of the continental block. So Tectonic was able to use a plastic model to try to reproduce the same phenomena in first order. So in this model, the plastic thing that you are seeing here is made by the material that can be deformed in terms of the in a brittle way, whereas this block, the black wooden block, mimic the extent of the Indian plate that is a very rigid block that do not contain any of the deformations. So as the block extruded or the indented into the plastic block, you can see the first block extruded, and then the second block started to extrude, and there are several major active folds, mainly stressy folds, exist in this area. However, starting from the mid to late 90s, when we're starting to have a lot of GPS velocities in the interior of the Asia, we started to see a different phenomena that you can see from this GPS velocity pattern, that those the GPS velocity was referenced to the stable Asia plate, which is in the Siberia area, that those GPS vectors showing that the southern part of the Tibetan Plateau is deeply affected by the indentation of the India plate. However, around this area, which is the area that we call the Eastern Himalayan Syntaxis, we can see there is a strong rotation, clockwise rotation happening around the Eastern Himalayan Syntaxis. Not only just the rotations, but also the length of the vector, which means the velocity, decreased from about 2 centimeters to the south and to the eastern Myanmar, southern Yunnan area, the velocity has been decreased to less than 10 millimeters per year. So this kind of phenomena, and also the change of the topography from the eastern Tibetan Plateau to the Sunda Plateau area, starting to let people think maybe the crust is not deformed in a very rigid way. Instead, maybe the material in the crust can somehow have some kind of flowing deformations. So based on this kind of physical interpretation, first order physical interpretations, Clark and Royden in 2000 published this very well-known paper saying that maybe the deformation of the Tibetan Plateau and the Sunda Plate is not controlled by the rigid plug extrusion as Prof suggested in 80s. Instead, there is the lower part of the crust where the feldspar and quartz is under the high temperature and the pressure can start to deform in a ductile matters. So if the lower part of the crust have a lot of the ductile deformation, then what may happen is that the material that being thickened, the uplift in the Tibetan Plateau and starting to flow from the Tibetan Plateau toward the south and forming a topography that gradually decrease its elevation from north to the south. And this kind of phenomena they were trying to use to explain the deformation on the surface. For example, this the lower part is a figure published by Clark et al. In 2005, and this profile is right around here across the Longshan thrust belt to the Sichuan Basin. The Sichuan Basin is a very strong rigid block because it's a very old continental block that now has been stuck in the middle of the Asia plate. So their interpretation of the changing of the topography and the formation of the Longshan fold is completely due to the channel flow that happening at the depths around 30 kilometers below the surface. And because of this channel-like extrusions, uplift the topography and forming the major boundary fold at the boundary of the Sichuan Basin. So, after this long description, now we know that around the eastern Tibet to the northern part of the Sunda Land block, basically there are two different end models trying to use completely different mechanism to explain the deformation of the northern Sunda Plate as well as the Tibetan Plateau. So the model to the left is the old model that proposed by the French group, where they believe that the entire crust, all the way from the surface to the mohole, is a rigid block. So all of the deformation was kind of accumulate or adjust by the major plate boundary fold. Whereas the model to the left believe that most of the deformation is controlled by the flow of the lower crust, and the topography is just passively passively moving above, just like an eye sitting on top of the flowing river. So it's passively moving on top of this flowing river and forming a series of the distributed deformations. So this is the first order story, but which model is correct or not is actually require a lot of the geological and the geophysical observations. So one of the important observation is that how can we determine the major fault slip rate? And if we can see anything from earthquake distributions along the major fault system or along the median of the continental crust. So let's look at one of the examples that extend this argument. So the Argentine fault is one of the major stressy faults in Central Asia, extending to interior of the China. And this fault, in the to 40 to 50 years ago, when Prof first drew his tectonic map, this fault was act like a major block boundary fault, separating the white block and the Southern China yellow block. And if everything is deformed in a very rigid way, follow the idea of the block extrusion, then this fault should accommodate a very high geological slip rate since the extrusion of the block. And in some place, for example, in the 2004 paper, they are using the channel offset on top of the fault, across the fault, to determine the slip rate of the fault. And they find out that the Argentine fault may slip at a rate, in average, around 2.5 centimeters per year, matching to the idea from the blocks extrusion model. However, if you are using the GPS to determine the decadal slip rate, which means that the slip rate that we can only observe in the past 20 to 10 years, the result from the GPS velocity only show that the Argentine fault accommodate the slip rate less than 1 centimeter per year, which is only about 1/3 of the rate suggested by the geological studies. So if the Argentine fault only received less than 1 centimeter per year of slip rate, then where were the other slip goes? And then, of course, one hypothesis is that they were distributed in the median of the continental crust, which means that the deformation is distributed. And that's a model supported to the crustal deformation or channel flow deformations. So even nowadays that we have a lot of different observations, as you can see from these examples, it is still under a very big debate whether the Indian and the Eurasian collision system is under the control of the block extrusion, nor is under the control under the channel flow deformations. And a recent study in the Argentine fault shows that, in fact, the story probably fall in the middle of these two members. For example, T et al. 2022's paper, they find out the Argentine fault slip rate may be reached to about 1.2 centimeter per year. About 50% of the strand that had been reported in the early paper using the channel offset across the fault, and it's about 1.5 times higher than the slip rate suggested by the GPS study. So maybe, in fact, what we're looking at for the Indian-Asian deformation is a kind of a combination between the flow and also the blocks extrusions. Let's look at another example that's happening in the Sichuan Basin. This example will show you how this kind of idea of the tectonic model affect to our interpretation of the crustal deformation or even the whole structure systems. So both of these two profiles were the same, were drawn at the same location, which in fact the western margin of the Sichuan Basin across the Longmenshan Fault system. And as you may know that the Longmenshan Fault system is the home of the 2008 Wenchuan earthquake. It's a magnitude 7.9 earthquake. The upper part of the model showing that the Precambrian material is kind of tuned to the surface because of the pushing from the channel flow in the middle, in the lower to middle part of the crust. So it's just like you are using your toothpaste and you are squeezing your toothpaste so that your toothpaste will start to push the material in front and forming this kind of welding force and assume the Cambrian massive to the surface and forming the Longmenshan Fault system in front. However, the figure B in the lower part of the panel shows a completely different explanation that most of the deformation, actually all of the deformation, is controlled by so-called fault band fault deformation. And These two models, although both of them seems to be able to understand the surface geology, however, they have a completely different implications. For example, if you are using a fold-bend-fold model to try to explain the formation of the Lomanshan Fault, this model actually requires a lot of shortening happening in the western part of the Sichuan Basin. The amount of shortening may reach to about 30 or even larger deformations. However, if you believe the crustal flow is a major cause of this kind of tectonic deformation, then you don't need a lot of the shortening happening on the surface. Instead, you only need to have the material floating to the top, exhumed to the surface of the crust to forming this kind of features. So in terms of the long-term deformation, these two different models would have a lot of different interpretation or implication in terms to our understanding about how the Asia was deformed or how the plate tectonic system interact to each other in the around Eastern Himalayan Syntaxis. So let's look at the global seismicity around the Myanmar to see if we can find any kind of the feature associated with these different deformations. So this map showing right here is a compilation from several different data sets. So all of the color dot, except for the green color dot, is from the global seismicity for the magnitude 5 and above earthquake using the global catalog. And the green dot is collected from the Chinese seismic network as well as the Thailand seismic network for the magnitude smaller than 5 earthquakes. And you can see that, in fact, although there are several earthquakes happening in the median of the continent, the majority of the seismicity actually happen forming a linear feature on the map. For example, we can clearly see that from the northern part of the Sagaing Fault to the central part of the Sagaing Fault, this seismicity delineate the location of the Sagaing Fault in the first order magnitudes. Along the Himalayan mountain front, there are several clusters of the earthquake that's showing that there is a very big thrust fault underneath the Himalayas. And as you may notice that this cluster right here is associated with the Nepal earthquake in 2015, whereas there are other cluster earthquake, for example, this one is likely to be associated with the earthquake happened in 1946. And there is another very big cluster here, and we are going to talk about this event in a later part of the conversation. And just south of the Sichuan Basin, this kind of linear deformations, linear alignment of the seismicity do exist in the interior part of the southern China block. For example, here you can see there are a bunch of seismicity going on. Those seismicity are mainly along the boundary, mainly along the Xianshui and the Xiaojiang Fault system. And there's another group of seismicity all the way going down here, and you can see that the Red River Fault right here stop all the seismicity and forming a seismic gap along the Red River Fault. The eastern Myanmar and the northern Thailand, the situation is getting a little bit more complicated. That in the big earthquake, for the big earthquake, we do see this kind of lineation. For example, these are the earthquake cluster associated with 1988 earthquake. This is the cluster of earthquake associated with the 1976 earthquake. However, there are also some earthquake cloud that happening in the northern part of the Thailand, which may be affected by the very dense distribution of active fault, as well as a poor earthquake location determined by the Chinese seismic network as well as the Thailand network in the early days. Now let's look at the major tectonic elements in this area on top of this seismicity map. So this is the main Himalaya thrust that I already mentioned to you. This is the home of the giant earthquake in between, near the border of India and China, as well as in the middle of the Bhutan and the Nepal. Those features offshore are representing the seismicity associated with the Sunda megathrust, as well as the element C spreading center over here. And the low seismicity in the central Myanmar are associated with the Sakha impulse system. And these earthquake clouds are mostly associated with San Plateau fault system, Red River fault, and Xiaojiang fault system. So how about the GPS velocities? Are we able to see such kind of distinct change of the GPS velocity across the major fault? I think we do. But of course, there are also some deformation. Doesn't look like it's a sharp contrast across the major fault. So the first thing is that, of course, on this map, is all of the GPS velocity is referenced to the Eurasia reference frame. That means that we assume that the plane motion of the Eurasia control the rigid block deformations. So the velocity you are seeing is relative to this rigid block movement on the crust, how the ground was deformed. That's why inside the stable Eurasia, the GPS velocity vector are very short, whereas on the Indian subcontinent, the GPS velocity is very long. So in this map, you can see that across the Himalaya frontal thrust, we do see some kind of shortening happen, but the shortening happening is kind of a gradient. This may have something to do with the lock-in depth of Himalaya frontal thrust, and I believe Eric Lindsay, which is going to give a presentation probably 2 to 3 weeks later, he's going to talk about details. Across the Lomanshan fault, we'll also see such kind of gradient happening. The GPS velocity is changing from about 4 millimeter per year to almost 0 across the Sichuan Basin. And here, there's a very clear gradient happening in between the place from Chengdu to Kunming, and that's basically follow the boundary of the Xiaojiang fault. You can see there are less GPS velocity covering the interior of the Myanmar, because when this data set was published, there are not a lot of the benchmark in Myanmar has been resurveyed, nor there are a lot of the scientific network has been deployed. But the situation has been changed in the 10 years that at least now we have more GPS vector to covering this part to understand how the plate system deformed in this area. And now let's changing the reference frame. So all the data that you're seeing on this map, in fact, are the same data as we showed in the previous map. However, what you can see is that the vectors, the length of the vector change, and the direction where the vector is pointing to also change. This is because now we are not using the Indian as a major reference frame. Sorry, we are not using the Eurasia as a major reference frame. Instead, we use the India's subcontinent plane motion as a reference frame. So now all the GPS velocity is referenced to the India. And this map, you can see very clearly that between the border of the China and India, the plane motion vector become very, very short. Means that the southern part of Himalaya in the past 10 to 20 years basically move along the Indian plate, which means that this part of the thrust fault is almost completely locked. And toward the Myanmar side, that we are seeing those vectors in the Rakhine range or the Indo-Burma range moving toward India with the length of the vector up to about 15 millimeter per year. So this indicates that offshore the Western Myanmar, the fault, in fact, are accommodating a lot of the motions to forming convergent plate boundaries. And of course, in other part, you can see the vector become very, very long. That means from here, from Yunnan to India, there are a lot of motion. It's accommodated by this kind of deformation. So we zoom in further into the eastern flank of the Indian Eurasia collision system. This is what we are seeing. So the Indian plate relative to the stable Eurasia is moving toward north at a rate about 3 to 4 centimeters per year. And this kind of motion basically can decompose into two major strands across the western boundary of the Myanmar and also the eastern boundary of the Myanmar block, which each of them absorb about 2 centimeters per year strand. And in the north, because of the Indian plate collisions, the materials from the eastern Tibetan plateau are moving toward the south, which is kind of secondary extrusion along the southwestern boundary of the Sichuan Basin, along Xianshui He Chaojiang Fault, and that actually affect to the active fault deformation in the northern part of the Sunda Plate. So all the deformation we are seeing in the eastern Myanmar to the northern Thailand as well as Yunnan is constrained by the interaction of all these plate motions. And under these kind of conditions, there are a lot of the main disaster earthquake happening in this area. Here are just several examples that I pick up today. So the largest earthquake, in fact, was happening in the corner of the Himalaya, in the very northern edge of the Myanmar, which is a corner of the Assam Valley, and that's the 1950 Assam earthquake. The magnitude may reach to magnitude 8.7, and that make the 1950 Assam earthquake the largest earthquake ever happened on land. So offshore, of course, offshore we may have an even larger earthquake, but the Assam earthquake remaining the king of the earthquake on land. And other than the Assam earthquake, there are also a very big event happening in the northwestern part, close to the northwestern border of the Myanmar. That's the 1897 Shinlong earthquake. The magnitude may also reach to about 8.1 to 8.3 in terms of the moment magnitudes. And in the Shan Plateau area, we have the 1976, 1988, 1912. And in the recent year, after the 21st century, we have the 2011 and 2014 earthquake close to the border between Myanmar and Thailand and caused a severe damage in that area.